Okay, so today we're looking at 2.4, which is functions and mathematical models. So I know a lot of students really enjoy this section because we start to kind of touch in more to the real world. I want to be clear that functions don't always have to be real world phenomena. They can just be mathematical structures, and there's a lot of actually amazing stuff that comes from that. So I don't want to undersell that, especially those of us who are heading more into mathematics. But for those of us who are maybe more interested in business or hard sciences or soft sciences, models are a great way to simplify and represent things that are just happening in the world. Sometimes to an amazing degree, how accurate they can be. But again, it's the power of abstraction, of simplifying out the unnecessary information or things that maybe have limited impact and just focusing in on the important parts. And so what we know about functions, right, is that we have an input that's dictated by some rule and goes to exactly one output. And can we represent a given description with this notation in the proper order, right? The input and output are going to be different quantities. They're going to be related to each other in some way. But what makes sense to be what we call the dependent or output, and what makes sense to be the independent or input? Again, independent meaning it kind of acts on its own accord, and dependent depends on that value. And we also use the letters X and Y here often to correspond. So we're going to look at a few examples of descriptions, and we're going to figure out what's the best way to represent this with inputs and outputs. What would be the most logical or natural choice to choose for an input variable and for an output variable, and the other way around, if given a mathematical notation, can we translate that into a verbal description? Again, being able to communicate our ideas clearly in math is a super important skill. I've said this before, that computers can do a lot of the interesting and computational stuff for us, which you probably are familiar with. There's a billion apps out there that can do a lot of the things that we do, but the real power comes from truly understanding and being able to communicate what those findings mean. As well as, right, we need to have these skills to actually understand the language of math. So, with that, let's dive into an example. Okay, so here we have a question of which is the more natural choice for the input or output. Remember, we'd use the language that the output is a function of the input. And so given maybe two variables or a description of a situation, which is which? And sometimes it could go either way, but oftentimes there is a more natural choice. So, let's say we're given this description, that the number of calories burned are measured in relation to the length of a workout in minutes. Now you might have some intuition of what the input or independent variable might be and what the output or response variable might be. But let's work through this as if we're coming to it fresh. So calories burned, I'm seeing this and I'm thinking this is an amount, right? This is a number, and I might call this C for calories burned. We don't need to give it a variable right now, but that's okay. Are measured in relation to the length of a workout in minutes. Length of a workout in minutes also sounds like a number. And I might call that T for time. So we've got two quantities identified, the number of calories and time in minutes. And so the question is the number of calories a function of time spent during the workout, or is the amount of time during the workout a function or depend on the amount of calories burned? So it's more natural to see often that time is often, I want to say this clearly because it's not always the case, often a natural choice for input or independent variable. And the reason for that is because time typically doesn't depend on anything else. Time is kind of doing its thing and marching onward. And other things can change in relation to time or in response to time. So time is often a very natural choice for input or independent. And I'd say the same thing here, right? The amount of time you're working out, we know that calories are being expended in that way during that window of time. So that's one way to think about it. So we might say that the number of is a function of time spent working out. And we want to give a rationale on why this makes sense. Okay, so we would know that for a given person, time working out will only give one expenditure of energy in calories. And then maybe let's think about why it wouldn't work the other way around. Right? So why is it that calories burned are a function of time spent working out and not the other way around? So is time spent working out a function of calories burned? Well, you might be able to come up with a way where you say, well, I want to know how much time I worked out based on the calories burned. Maybe you've got a Fitbit or you've got some type of biometric tool, but that's kind of a less natural way to view this, right? Because if you're wearing a device like that, you probably already know how long you worked out. And so there's that. It's not as natural a choice, but there's also the problem of the definition of a function that we need to worry about. So let's consider, let's say why not the other way around? Why is it not that time working out isn't a function of the calories burned? Well, I see one obvious reason, which is that if I burn 300 calories, I could do that in a 30-minute run or a 60-minute run. Or there could be several other ways we could get there, right? If we think of the input of 300 calories and then how long it takes to work that out, it's really a question of now like intensity, right? So that changes things. So this would result in having multiple outputs per input. This results in multiple outputs per input. Therefore breaking the definition of function. So it wouldn't make sense, or it would be more of a kind of hassle, or there'd be more jiggering needed to make this time working out a function of the calories. It makes more sense that the amount of time working out is going to give you how much energy you spent in calories. Again, there's a question of intensity that could be put there, but this is just the more natural choice. And so what we would say here is that calories burned we would say the amount of calories burned is a little bit better English. Time spent working out. Is a function of the time spent working out. Right, here's my input, and here's my output. Output is a function of the input. So that's what we'd be looking for here, again with some sort of rationale for why this way and why not the other way around. Okay, so this is not meant to be cookie cutter. Obviously, the rationale for time working out and calories is going to be different for the amount of time for something to ferment and the number of yeast you use, as well as the amount you get paid versus the size area that you just cleaned. Whatever it might be, it's going to depend on the context. So that's why I say, appeal to your common sense, appeal to your background knowledge of the world to make arguments for this. Don't kind of just keep it in math land. So kind of keep it in the real world as best you can. And it does take some thinking. So this is challenging because I think typically in math courses there's a lot of symbolic manipulation and calculation and not a lot of communication. So this is kind of a new skill. So give yourself some patience and remember that this is going to feel kind of different. So this is an example of how we would choose from a given description what would be input and what would be output. Time is a natural choice for input. It's not always the case. So I'll give you one more example of how I see that. Okay, so here's another example. The time for an organism to mature is related to the amount of calories it's consumed. So we might be looking at something like a moth or a butterfly going into a chrysalis. We might be looking at a salamander or something like this. The amount of calories it consumes is going to dictate how long it takes for this organism to reach its mature state. We might, think about an organism that's been starved is not going to be growing as quickly. So there is a natural fit here to me, which when we identify the two quantities, time for an organism to mature, we might give that some value t, and the amount of calories it has consumed over its lifetime, c, it seems that the time would depend on the calories consumed and not the other way around. All right, so let's jot this down. So it would seem that t is a function of c. This is the input, calories. This is the output, time to mature. So we would say that, the time for an organism to mature is a function of the number of calories it's consumed. So why is this a natural fit? Well, it would seem that the number of calories consumed is independent, right, of the time it takes to mature. I think you'd have to jump through a lot of hoops to make that case as not being true. So the number of calories being consumed is independent of time to mature. And the time to mature and grow certainly depends on nutrition, as we'd know from biology. Biological concept. Okay, and so the question is, why not then, why isn't calories a function of the time it takes to mature? Well, let's think about it. Well, the first way I see it is looking at the calories, like we said above. Calories consumed is independent of maturity time. Right? This is something that depends on the environment. And the other reason might be that you could have a given time. Let's say it takes 1 year to mature. And that might, for the same species of organism, get mapped to, from F, to two different outputs of maybe, 20,000 calories to 20,001 calories. Right? So here you have a problem where you've got the same input time going to two different outputs, and that breaks the definition of function. So that's just clearly a less natural fit to go this direction. Where here we can see the time for an organism to mature. From biology, we would know or expect that that's going to be a function of the calories it's consumed. So here's an example of where time is not the clear input choice, but instead a clearer output choice. But you got to rely on maybe some other disciplinary knowledge, some common knowledge that comes from other fields. So now that we've taken some time to identify inputs and outputs, and we've played with a little bit of notation, I've kind of teased it in there, I want to take us specifically into moving from mathematical function notation and rendering that into a sentence. What does this mean in terms of the model, in terms of the real relationship? So if we go back to our first example and we say that the number of calories burned in hundreds is a function of the length of the workout in minutes. And then we're given a ordered pair or a function pair. What does this mean? That's what this interpret statement means. What does this mean in English? F of 15 equals 2. Well, we need to do a few things. We need to remember that this represents an input-output pair, right? Where does the input go? F of the input equals output. So my input is 15, my output is 2. So what does that mean in terms of the relationship? What's my input variable? What's my output variable in the model? Well, we said the number of calories burned is a function of the length of the workout in minutes. Well, if something is a function of something else, that means what it's a function of, this is the input, and this is the output. And that makes sense from what we said before, that the number of calories you burn depends on how long it is. So input is length of workout in minutes. So we can start to render this into speech here. So this really means that a workout of length, I'm going to write it out kind of jumbly at first, and then we'll write it out better. A workout of length 15 minutes results in, because that's our input, and then our output is what? The number of calories burned in hundreds. So I've gotten 2 here, so that means results in 2 times 100, 200 calories burned. Okay, and again, that's a fine sentence, but we could write this a little bit more naturally and say working out for 15 minutes equates to 200 burned calories. I'm mainly just trying to show you that there's a lot of different ways to write this and go with what's the most natural. The less math jargon we can use, the better when we're talking about interpreting. Okay, so let's do one more here. Okay, so one more here. The amount of medicine prescribed in hundreds of milligrams is a function of the pain level reported by the patient. So what does 5 equals f of 6 mean? Again, this is an input-output pair, and it means something in terms of the model. But we need to know what's the input and what's the output first. All right, so we know that this is my input. We know that this is my output, just from the function notation. And then in terms of the description given, what's the input and output variables? Well, the amount of medicines prescribed is a function of the pain level reported. So if something's a function of something else, that latter piece is what the input variable is. So the pain level reported is the input on a 1 to 10 scale, and the amount of medicine prescribed in hundreds of milligrams is the output. So this really means, right, 500 milligrams of medicine, and this input variable must mean 6 out of 10 pain report. So now that we have these quantities identified, now it's time to construct a sentence on what this means. Okay, and so what we say is that a report of 6 out of 10 on the pain scale will result in a prescription of 500 milligrams of the medicine. Okay, so here is my output. Here is my input. But again, this part is really just about making a sentence that comes off naturally and is clear, right? Somebody who's not in our math course could understand this, whereas somebody who isn't in our math course probably wouldn't get what this means. So just to recap briefly, today we were looking at translating between a description of a model and the function notation, taking care to note what's an input that makes sense for a given output and vice versa. We need to make sure that our input is only being mapped to exactly one output. Getting the order down with the function notation as well as the verbal description. And then again, taking some time to think about what's the most natural choice. So these do require a little bit of contemplation. It's not a quick fire thing, and you might be able to talk yourself in and out of certain choices, and that's a good thing. As long as you have a solid rationale for what you've chosen as input and output, everything else should flow. And again, if you're worried about partial credit, things like this, for a well thought out argument, I typically award full credit for this because that's what we're looking for. Does it make sense that something's an input versus an output? And then how can we describe the relationship given the mathematical notation like we've seen here? Okay, so that's it for today. There are some more worked examples in the notes sheet for this section, and I encourage you to definitely go check those out.